Okay, so section 1.5 deals with solution sets of linear systems, and I'd like to get right to an example. Okay, so I'm going to give you a moment to copy this example down, and then we'll go over it. Okay, so here we want to, well, we have two systems of equations here. We have two systems, and we have a homogeneous system and a non-homogeneous system. The two systems almost look alike, but what's the difference between these two systems of equations? That's right, Andres. The first system of equations has has zeros on the right side after the equal signs. Okay, the first system of equations has the zeros, and the second system does not. You have a 9 there on the second equation. And so the second system of equations is called a non-homogeneous system. Now, what we want to do is we want to describe the solution sets for each of these systems. Okay, we want to describe the solution sets for each of these systems. So let's focus on perhaps the easier system of equations, this first system. Now, geometrically, what do these equations describe? We have two equations. Geometrically, what do they describe? Good, good. Ben, Nafoni, and Natalie, very good. Two planes. Now, we're used to, of course, X, Y, and Z, but for X, Y, and Z axes. But in linear algebra, we have X1, X2, X3 axes. And the two planes, if there were a solution to this system of equations, what would that tell us about the two planes? If we found a solution to this system, that would mean, good, Hung, good, Catherine, the planes intersect. If the planes intersect, what would they intersect in geometrically? That's right, Catherine, a line. Unless, of course, the two equations are ultimately the same equation. If the two equations are redundant, then the intersection of the two equations would be not a line, but a plane. That's right, Hung. It would be a plane. Because that's all you'd have. You'd have one, if one equation were like, if one equation were a multiple of the other equation, the two equations are the same equation. They're redundant, and that means you have one plane. Okay, and so, all right. So what we want to do is solve the system. So, okay, we're going to do that. First thing we'll do is we'll set up our augmented matrix. And then we're going to do some row operations. And how many of you feel like, hey, how many of you feel you're pretty good with row operations now? You're feeling comfortable with the row operations. Okay, Eleanor, Nafani, Hung. All right, so you're experts now, right? Natalie and Lewis, yeah, you're experts. All right, so you know, I showed what row operations I was doing here on the right. So, I mean, ultimately, the goal is to get the augmented matrix in this form here. By the way, what's this form called? What's that called? What form is that augmented matrix in? Good, reduced echelon form. Good. That's right. Thank you, Hung. Thank you, Catherine. All right, so let me give you a moment to copy that. Okay, so all right, so just of course, you know how I write row operations. So going from the first augmented matrix is equivalent to this second augmented matrix. And what I did was I multiplied the first equation by -2, added that to the second equation, added that equation to the second equation, and replaced the second equation with the result. So -2 times row 1 plus row 2, put that result in row 2. All right, and then of course the third instructions here, I took the second equation and scaled it by multiplying by -1/9 and replaced the second equation with that result. And then finally, to get to the final, to get to the augmented matrix in reduced echelon form, I took the second equation times -4, added it to the first equation, and replaced the first equation with that result. And so here's the solution. We have a free variable, right? It's going to be a consistent system. We have a free variable. Okay, so I let x3 equals be the free variable. Then x2 will equal 2x3 and x1 will equal -3x3. Okay, so are there any questions on this so far? All right, and this is let me just see here. This is what you learned in section 1.2, of course. We talked about free variables. And, up to now, you've been getting solutions, and that's been fine. But what we're going to do now is we're going to take this solution and write it. Well, we're going to write it in a certain way to help us understand what this intersection looks like. I mean, we agree that the system of equations is consistent. That means that these two planes intersect in a line. But I'd like to know some details about that line of intersection. Well, the line of intersection has to uh, uh, I mean, given that we know that what the solution is of our system of equations, we ought to be able to discuss what the line of intersection is. In other words, we ought to be able to describe that line of intersection. So I'm going to show you how we do that. May I go to the next page? All right, very good, thank you. Okay, well, here then, I mean, I know x1, x2, and x3 is my solution, right? But of course, x1 equals -3x3, x2 equals 2x3, and x3 is just itself because x3 is a free variable. So the vector solution x can be, which is equal to x1, x2, x3, that can be written this way based on my solution. And from there, I can write the solution vector x in parametric vector form, where x3 is my parameter. Let me give you a moment to catch up here. Okay, let me give you a moment to catch up. Let me know if you have any questions. Okay, so what we've done is we have written our solution in parametric vector form. The parameter is x3. And so what I do, okay, is I take my solution and rewrite it in this form, which is a scalar x3 times some vector v. The vector v is negative 3, 2, 1. And this is very helpful because then we can see that the intersection of the two planes is going to be a line, okay, that's parallel to the vector v passing through the origin. So what I've done here in this picture, is I've drawn x1, x2, and x3, and I've drawn the vector v emanating out from the origin. Well, any multiple of v would let me ask you, what's the value of the parameter x3? Like I'm showing here a line. Maybe I can hold on here. Let me just, I don't want things to get too muddled up here, but one moment, class. Okay, here's this line. I call it line L1. And I'm saying that if I take the vector v and multiply it by scalars, different scalars, it's going to produce different points. But if I put all the points together, it's going to form this line L1 that you see here that passes through the origin and is parallel to the vector v. It actually goes through the vector v. So let me ask you this. The origin, what would the value of x3 be on this line L1, L sub 1, at the origin? What would the value of x3 equal? That's right, Benjamin, 0. Because 0 times negative 3, 2, 1 is the origin. 0, 0, 0. Okay. So this here corresponds to x3 equals 0. That point there. All right, let me pick another point. What about right here? What about that point right there at the tip of V? What is x3 equal to at that point on the line? What is the value of x3? Good, Hung, it equals 1. Because 1 times V equals V. Are there any questions so far? Let me pick another point right here. Okay. For that yellow point there, or this point right here, what would you estimate x3 to be? Good. Good, Hung. -1. Please let me know if you have any questions. Please let me know. Okay. I'll pick one more point. I'm going to pick this point right here. Okay. What's x3 equal to on that point there? Good, Nafani. 1/2. Good. So you see, as I vary the parameter, as I vary x3, I get different points on the line. And if you put all the points together, it traces out a line through the origin, passing through the vector v, or parallel to the vector v. And so isn't this, how many think this is pretty cool? Now you can geometrically describe what this line looks like. How many think that's kind of neat? Yeah, yeah. You know, you don't need to just say, hey, the intersection's a line. You can describe the line. You can describe it. Are there any questions before we move on? Okay. All right. Well, let us continue then. Let us continue. Now we're going to try to solve the non-homogeneous system. Okay. And the row operations that I'm using are exactly the same as the ones I used before. I can write them down though. Okay. Okay, so hopefully, let me just see here. One moment. Okay, and so now here is our solution. we have a solution. The two equations are equations of planes. We have a solution. So the two planes intersect in a line. But the line, of course, is different than the line we got for the in the homogeneous system. The non-homogeneous system gives us a line of intersection, but that line of intersection is a different line of intersection than the line of intersection was for the homogeneous system. It's different because the solution's different. But you're going to see that there is a connection. There is a connection. So what should we do with this solution? What form should we write the solution in to see what this line looks like? What form? Vector form. That's right, Benjamin. Vector form, parametric vector form. Okay, and so I will do that. I'll move to the next page if we're good. Okay. So here is our solution vector x. Okay. And x1 is equal, as we know, well, x3 is free, so x3 is just x3. x2 is negative 1 plus 2x3. And x1 is 4 minus 3x3. And look what I do here. I write this vector here as the sum of these two vectors. Okay. And so the solution vector in parametric vector form is going to be the vector x equals this vector p, this constant vector p, plus the parameter x3 times that vector v. And oh, that vector v, we saw that in the non-homogeneous system. The vector v was also negative 3, 2, 1. So we can describe the intersection of the two planes as a line L2, and I'm going to let you copy this down. It's a line L2 passing through the point 4, negative 1, 0, parallel or in the direction of V. Okay, let me give you a moment to catch up here. Okay, so what I've done is, of course, I've written my solution in the parametric vector form here. And in the picture on the right, okay, this picture here on the right, I draw the x1, x2, x3 axes. I draw the vector v, and the line L2, is going to be this line right here. Okay. It's parallel to the vector v, and it passes through the point P1, P, time the point P or the vector P, which is 4, -1, 0. So I mean, I guess I could hold on here. I guess I could draw. Oh, come on. Okay, I mean, I could. That's vector P. Okay. Okay. So understanding why the line passes through the point 4, -1, 0. Okay. And why the lines parallel to the vector v, it really helps to, well, you understand about vector addition and you understand about parameters. So let me ask you here, maybe what I'll do is, okay, so this blue point here, what is x3 equal to? What's the value of the parameter equal to for that blue point on the line L2? What does x3 have to equal if we're at the point P or the vector P? What does x3 have to equal? Well, Catherine, let's see. Look at your. That's all right. X3 would equal. That's right, Lewis. 0. And I think Catherine agrees. Because if x3 here equals 0, then the point is 4, -1, 0. Let's pick another point here. Let's pick this point right. Let me see here. One moment. I have to be kind of careful, but I'll just. What about that point right there? What would the value of x3 equal? For that point, approximately. Good, Nafani. 1. Good. And why is that? Well, I'll show you why. Because what you're doing from the origin, you're going out of vector P, and then you're adding a vector V. See that? You're going out a vector P from the origin, and then tip to tail addition, you're adding the vector V, and that gets you to that purple point. Is anybody uncomfortable with that? Okay, let's do one more point. How about right here? Whoops, hold on. What's x3 going to be approximately for that? What's the value of the parameter going to be for that point on the line? What's x3 going to equal? Approximately. Good. Good, Haley. Good, Catherine. 2. So you see, I believe in experiencing things. And so the book will maybe draw some nice pictures, and that's good. But, you know, I mean, I like to really understand it. Are you really understanding this now? Are you feeling it, what I'm trying to get at? Good, Abby, good. Good, and this motivates theorem 6 in the book. Let me bring up theorem, hold on, let me bring up the theorem. One moment here. I have to bring up the textbook, should have brought it up here, but one moment. Let's see, one moment, class. Hold on. Yeah, give me a moment to bring up the book here. I have it. I just have to get to the right section here. Hang on, I just got to find it, class. There we go. Put this down a little bit. Okay, so this motivates theorem 6. Let me get theorem 6 here. Theorem 6 says, suppose that the equation okay, we're in theorem 6. Suppose the equation ax equals b is consistent for some given vector b, and let the vector p be a solution. So the system of homogeneous, non-homogeneous equations corresponds to ax equals b. Okay, so in other words, like in the example, I gave you a non-homogeneous system of equations. I gave you a homogeneous system and a non-homogeneous system of equations, right? I mean, if we go back to, hold on here, the example. Okay. I mean, let's think of it like this. Okay, so the matrix A, is going to be, what would the matrix A be here? 1, 4, -5, 2, -1, and 8. Okay. And the vector x, okay, the vector x is x1. Hold on, class. Don't worry. The vector x is x1, x2, and x3. So what would the matrix equation be here for that first system of equations? What would the matrix equation be for that homogeneous system? Who can chat it out for me in the chat line? So it's blank, blank equals blank. So all I'm asking is, this is a system of equations. A system of equations can be written as a matrix equation. And I'm asking, what is that matrix equation? What's going to go in the first slot here? Good. And that's right, home. A x equals 0. Now, is that right, what I wrote there? Is that perfectly right, what I wrote there? Or is there something missing? So the matrix A is 2 rows by 3 columns. The vector x is, based on here, the vector x is 3 rows by 1 column, 3 by 1. So what should this product vector be, the vector 0? It should be, what are the dimensions on the vector? Good, it's a 2 by 1. That's right. And have I written a vector here? Is the 0 a vector? The way I wrote it? No, what do we need? What do we need, Nafani? What do we need above that 0? An arrow. Right, there we go. Okay. So, all right. Now I'm going to put another thing here, up here. I'm going to put a vector B. And I'm going to call that vector B 0 and 9. So, the non-homogeneous system, what would its matrix equation be? What would its matrix equation be? Good, Justin. A times X equals B. That's exactly right. Okay. Now, the reason I have this is because it's important to see this, to just connect that with for the theorem. Are there any questions before I go back to the theorem in the book? All right. Well, let me go ahead then. Let me just comment here. So for the homogeneous system, this is what the solution looked like in parametric vector form. X3 times the vector V. That was for the homogeneous system solution. The non-homogeneous system solution, in parametric vector form, the solution was a vector P plus X3 times V. Okay, so that being said, now let me go right to the book. And there's theorem 6. So suppose the equation AX equals B. In other words, suppose that's the homogeneous system, suppose the non-homogeneous system is consistent for some vector B, and let P be a solution. Then the solution set of AX equals B is the set of all vectors of the form W equals P plus VH, where VH is any solution of the homogeneous equation. Okay, and that's exactly what we saw. That's exactly what we saw for our example here. That's exactly what we saw. Okay. Are there any questions on theorem 6? How many maybe have taken differential equations? There's an analogy to theorem 6 in differential equations. Like if you have a linear differential equation and you have homogeneous linear differential equation where the number after the equal sign is 0, you get a homogeneous solution. I want to be careful how I phrase this. And then if you have a non-homogeneous differential equation, a corresponding non-homogeneous differential equation, the solution is going to be the homogeneous solution plus a particular solution. How many recall that in maybe if you took Math 282? How many recall like an analogous result here to theorem 6? Okay, Benjamin says it remembers it's very, very similar. Right, you have homogeneous differential equations and non-homogeneous differential equations. That's right, Benjamin. Derivatives are linear operators as well. So okay, just thought I'd try to make a little connection there, and for you. And that being said, I want to actually hold on here. There was another example I wanted to show you, and well, actually, there's a few more examples because I want you to feel, comfortable. One moment. Okay, let me go back to example 2 here. Okay, so example 2, hold on here. Sorry, I just got to find it. I'm going to turn this email off. I don't want my email. Hold on, class. Give me one moment here. I just got to find example 2. It's like broken up. Yeah, this is where I want to be. Okay, example 2. Okay, one moment, class. Just give me one moment here. Okay, one moment, class. Sorry. Okay, let me go out of there. Okay, so here, example 2, section 1.5, they say a single linear equation can be treated as a very simple system of equations. Describe all solutions of the homogeneous system. Okay, so here's a homogeneous system. The right-hand side equals 0. It says there's no need in the solution, there's no need for a matrix solution. You just solve for the basic variable x1 in terms of the free variables. Okay, so in other words, if you were to take this equation of the plane, and how are they, so like you could write that as 10x1 equals 3x2 plus 2x3. Okay, so this equation of the plane, 10x1 minus 3x2 minus 2x3 equals 0. You could write that as 10x1 equals 3x2 plus 2x3. But then, if you divide it by 10, you would get this. Hold on here. If you were to take this equation and move to the right-hand side, the 3x2 and the 2x3, and then divide the equation by 10, or I would like to say multiply by 10th, because multiplying by a scalar is a row operation. You'll get x1 equals 0.3x2 plus 0.2x3, with x2 and x3 being free variables. And so you can write your solution vector as you see here, and then I can break that vector up into these two vectors. And how many parameters do I have? How many parameters do we have here in this example? Good, Hung. You have two parameters, and x2 and x3. And so I can write the solution vector x, which is all the points on the plane. I can write that solution vector as a linear combination of the vectors u and v. And if you were to take any linear combination of vectors u and v, as you see in figure 2 on the left, that's going to, all linear combinations of the vector u and v will trace out a plane in three-dimensional space that contains the vectors u and 3. Hold on, did I lose my, hold on, let me get it back. One moment. Please. Hold on, class. One moment, class. Okay, so like I said, the solution vector x, which consists of all the points on the plane, can be written in parametric vector form as a linear combination of the vectors u and v. And geometrically, in figure 2 here, all linear combinations of the vector u and v will form a plane in three-dimensional space that contains the vectors u and v. How many think, so you see what you're doing now? You're able to actually geometrically describe what these planes look like in three-dimensional space. by writing the solution, the solution vector for the plane in parametric vector form. Okay, so how many of you, hold on, I got to find my, how many of you think that's absolutely cool? Yeah, that is wild, Justin. That is wild. Eleanor agrees. Okay, so what I'd like to do, I'd like to give you a little time to work on the, I mean, for Thursday, you have section 1.4, some multiple choice exercises, and you have section 1.5, some free response exercises. So what I want to do is give you a little class time to work on the section 1.5. Let me stop the recording. Are there any questions at all?